Hello, guys. Very good evening, you all. Today I'm going to start with the topic the solutions from grade 12 chemistry. And here we go. Welcome to SPS Varsity. And I want you to support us by putting a like and then please comment if you have any suggestions. And in case if you like our video, so please subscribe to SPS Varsity. So I'm going to take you through the topic solutions. Let's start doing this. So whenever you say solutions, any kid will say what exactly is a solution. It's a mixture of two components, right? One is the solvent, the other one is the solute. Solute dissolves in the solvent to give you a solution. And the particles of the solute, they get distributed in the solvent. If solute and the solvent completely mix with each other, that's called as homogeneous solution. Like salt in water. Salt gets completely mixed with water, right? Salt dissolves in water and the solution is, the concentration is uniform throughout. And that's called as homogeneous solution. Homo means same. And hetero, it's different. Like you put in the sand in the water and sand particles are going to settle down. Sand doesn't dissolve in water. So the sand particles are going to settle down. This leads to the heterogeneous solution. So what we are going to speak is different type of solutions which we have and what are the properties of solutions. That's what we are going to discuss. And when you say solution, now whatever we are going to study, that's a binary solution. Binary in the sense there will be two components. One is a solvent, the other one is a solute. So what are the types of solution? Have you ever thought of this, that there are so many types of solution around you? The first one is a gaseous solution. Yeah, it is also a solution. When you the solute is also a gas, solvent is a gas. For example, the air which is around us, oxygen and the nitrogen, they mix completely. And then you have liquid which is present in the gas. That's two different liquids. This is separate from colloids. Don't get mixed with that. That's a heterogeneous solution. And we are going to speak about the homogeneous solution over here. The liquid in the gas, and then we have solid in the gas, camphor and the nitrogen. Camphor is a solid and the nitrogen is a gas. And the liquid solution, which are gas and liquid we have, that's oxygen in water. That's a dissolved oxygen. That's how the aquatic species live. Then we have two liquids, liquid mixture. We can say so many things when we come across liquid solutions. Ethanol, that's alcohol and water. Then you have the solid which is in the liquid. For example, salt in water, sugar in water, etc. Then we have to say about solid and solids. Gas in a solid, that's a solution of hydrogen over palladium. This is a hydrogenation catalyst. And then liquid in a solid, sodium mercury amalgam, which we use in different reactions. And then solid in the solid, that's copper dissolved in AU. So this is some of the examples of different types of solution, guys. If you're watching, please support us. And if you have any doubts, please put them in the comment section, okay? Yeah. I'm going now we are going through this one, the concentration of the solution. How do you express the concentration of the solution? So there are different terms. Whenever you say solution, we express the concentration in varieties of way, right? So if you have any, what do you say that, the tablet or any particular medicine, cough syrup maybe, at home, if you turn it, if you see the label, I mean the constituents which are present in that particular cough syrup, you see the W over W. That's a weight over weight, or W over mass over volume percentage. All of these are seen that. So how do you define these compositions or concentration terms? And the first one is the term, then there's a symbol or the unit which you're going to use, and the definition and the formula. That's what we are going to see in a simple way. Mass percentage, mass of the solute or mass of any one component divided by overall mass. This is how you find your percentages, right? In the top, you have your marks, and in the bottom, you have the total marks multiplied by 100. This is how you find out the percentage. The same way, the mass percentage of any component is equal to mass percentage of that particular component in the solution over the mass of the overall solution, or the total mass of the solution, times 100. Then you have volume percentage, and the volume of the solute or volume of one component divided by volume of all the components times 100. Since we are finding out the percentage, we have to multiply by 100. Don't forget that. Then mass over volume percentage. mass of one component, volume of the solution, that's the total volume, times 100. Or you can also say this as mass of the solute per 100 ml of the solution. This is another definition. And then parts per million. Where do you express this? Say if the components which are present in the atmosphere, for example, the carbon particles, the particulate particles whose concentration is very low in the atmosphere, then you are going to use the term ppm, stands for parts per million. You also have ppb, which stands for parts per billion. So what is parts per million? Number of parts of one component divided by total number of parts of all the components times, instead of percentage, that's 100, you're going to multiply it by million. Million is 10 to the power 6. So in other words, you can also express this as mass of one component over mass of the all components, or the total mass of all components, times 10 to the power 6 also you can do. That will also work. Then we have the mole fraction. What exactly is mole fraction? You should know how do you find out the number of moles over here. Whenever you see the number of moles, how do you write the number of moles, guys? Number of moles is equal to mass by atomic mass or molar mass. You can take any of this. If it is an atom, you calculate atomic mass. If it is a molecule or the compound, you calculate the MR value or the formula mass. So this gives you the number of moles of any component N. So if you have a mixture, then number of moles of one component divided by total number of moles of all the components which are there in the mixture. It can be one component, it can be Na plus Nb, or it can be Na plus Nb plus Nc. So how many components you may have, you have to add them up in the denominator. Here you don't have to multiply by 100. Be careful when you calculate it. And sum of the mole fractions is always unity. Xa plus Xb, if you calculate over here, so Xa plus Xb is going to give you what? Na over Na plus Nb plus Nb divided by Na plus Nb. And then it gives you Na plus Nb. In the denominator also it's Na plus Nb. So they get cancelled, and the sum of mole fraction is always unity. If there are more than 1, 2 or 3 components, then you can say Xa plus Xb plus up to Xn, which is equal to unity. Then you have two which are very important terms, the molarity and the molality. Molarity is number of the moles of the solute per liter of the solution. How much moles of the solute are present in per liter of the solution, that's called as molarity, and it's number of moles. What is the unit for number of moles? It's mole. Volume of the solution in liter, or this can be also in dm cube. So if you have some volume in centimeter cube, or if it is in ml, you have to divide it by 1000 and then you have to convert it into liters. That's how you do the calculation. Okay, and the unit can be mole per liter, mole per dm cube, or simply molar, capital M. Then we go for molality. Molality is a number of moles of the solute. The nominator remains the same. What changes? Per kg of this solvent only. You have only solvent in the denominator. In the previous expression of the definition, you had volume of the solution. Now it's mass of the solvent. How do you get the mass of the solvent? Mass of the solution minus mass of the solute is going to give you the mass of solvent. That's how you calculate. And the unit can be mole in the nominator per kg. Mole per kg can also be the unit. If it is given in grams, the mass, then what you do? Divide by 1000 and convert it to kg. And the unit for molality is small m. I think you are getting what I'm explaining. Then what do you have next? Among all these units, wherever mass comes, that is independent of temperature. Because though you increase the temperature, the mass is not going to change generally. And if you increase the temperature, what happens to the volume? So say you have water, you increase the temperature, water becomes vapor. So initially it was a liquid, now it is a gas. Volume, the expansion takes place. So the volume increases. Volume is in the denominator. So do you remember this? Mass is equal, molarity is equal to number of moles of solute divided by volume of the solution in liter. When you increase the temperature, volume of the solution increases. When volume increases, molarity comes down. So this you have to remember. Molality, ppm, mass percentage, and mole fraction. All these have the mass units. So these are temperature independent, whereas molarity is temperature dependent. With increase in temperature, the volume increases, and volume is in the denominator. When the volume increases, molarity is going to come down. Okay. Then we have a couple of problems which you can really quickly solve all these things. Calculate the mole fraction of ethylene glycol, and so be ready with the calculators. Or I can tell you how to solve the problems, but I don't give the values because you can solve in a better way since you are in the end of the year and you know how to calculate all these things. Calculate the mole fraction of ethylene glycol. So one of the component, whenever the mole fraction given problem is given, I always suggest you make two columns. That's the best way. Or you can deduct at the end this by 1 also, because the sum of mole fraction is a unity. Ethylene glycol, that's the formula is C2H6O2. The carbon has a mass of 12. I'm roughly taking the masses. Oxygen has 16 as a mass. So, and they have given, these are the atomic masses. You can see what I'm writing, correct? These are the atomic masses. If you calculate the molar mass, that's 12 times 2 because there are 2 carbons, 6 times 1 because there are 6 hydrogens, and 2 times 16 because there are 24 plus 6 plus 32. That's going to be 62. So 62 is the molar mass of ethylene glycol. And in a solution, so the molar mass of water in a solution, in the sense rest, will be the water solution. So you have the molar mass of water as 18 grams per mole. Now you calculate the mass over here. They have given 20% of ethylene glycol. In 100 gram of solution, 20 gram will be ethylene glycol, 80 gram will be water. Now you find out the number of moles. Number of moles of ethylene glycol, I'll take it as E, which is equal to mass over molar mass. That is equal to mass is 20 over 62. And here I'll take it as NW. NW is mass over molar mass. Let us quickly calculate these values. So it is not going to take much of our time, and we can solve so many problems really quickly. So this is going to give you 0.3225. I'll take up to 2 decimal places. And the next one, 80 divided by 18 is going to give you 4.444. So I'll take just 4.44. Now you calculate XE, mole fraction of ethylene glycol only. So Ne divided by Ne plus Nw. That's 0.32 divided by 0.32 plus 4.44 is going to give you 4.76. That will be 0.0067. If you want to calculate this too, you can calculate XW. You can calculate it as 4.44 divided by 4.44 divided by, you can also calculate this way, 4.7. Now it will be 4.44 divided by 4.76. This will be 0.9327. Or you can also do sum of mole fraction is unity. That's Xe plus Xw is equal to 1. So Xw is equal to 1 minus 0.0067. This also you can do. Whichever is convenient for you, you can do. But they have not asked the mole fraction of water. But in the flow, I explained it. Calculate the molality of ethanoic acid in 75 gram of benzene. So what do we calculate? What they have given? Mass of the solute is given. That's the ethanoic acid. 2.5 gram. And what is the formula to calculate molality? They have asked a molality. First you find what exactly you have to find out and what is given. Molality, which is equal to number of moles of solute over mass of solvent, just the solvent in kg. So how do you find out the number of moles of the solute? You have to find out the mass of the solute and also molar mass. I'll take it as MR of solute is equal to, the formula is CH3COOH. So there are two carbons. So 2 times the mass of carbon, that's 12, plus 4, there are 4 hydrogens times 1, plus there are 2 oxygens, so 2 times 16. So it's 24 plus 4, so it will be 60 gram per mole. Now the number of moles of the solute is equal to mass of the solute divided by molar mass of the solute. Overall mass of the solvent, they have given, can you see that? Mass of the solvent, 75 gram of benzene. 75 gram, how do you convert it into kg? 75 divided by 1000, that's going to give you 0.075 kg. You divide it, 0.075 kg. So when you divide it, let me quickly do it. So 2.5 over 60 over 0.075. That's going to give you 0.55 molar, small m. I hope you got it. This is one more question which is a bit tricky compared to the others. So calculate the mass of urea required to make 2.5 kg of 0.25 aqueous solution. So how do you find out? What do you have to find out? Mass of urea. This is what you have to find out. Forgive me if my handwriting is bad. I'm going in a flow. And you know the molar mass, right? MR. How do you calculate the MR of urea? Molar mass of urea. There are 2 nitrogens. So 14 times 2 is 28. Plus there is 1 carbon, 12. Plus there is 1 oxygen. Plus there are 4 hydrogens. So it is 28 plus 12 is 40 plus 20 is 60 gram per mole. What's the question? You have to make, they have given the molality as 0.25 molar. How do you calculate the molality? Molality is equal to number of moles of solute over mass of solvent in kg. So what is that you are going to calculate now? The moles. How do you get the moles? If it is a 0.25 molar solution, that means it has 0.25 mole in 1 kg solution. Sorry, 1 kg of solvent. That's how you find out, right? Now, what you calculate is, they have given 2.5 kg. So if it is 0.25, so if it is 0.25 mole times 60, that's going to give you the mass, 15 gram. Do you get this? Because the number of moles is equal to, how do you get the number of moles? Moles is equal to mass over MR, molar mass. If you calculate that, you are going to get the mass as this much. Now, what is the total mass of the solution? So you had 1 kg of the solvent, that's 1000 gram plus 15 gram. This is equal to 1015 gram. Now, 1.015 kg of solution has 0.015 kg of urea. This is according to the values which we got. So You can convert it into you can retain it in grams also. So they have asked 2.5 kg of the solution is going to contain how much? So it's 0. Or you can retain it in grams also. If you are going to retain it in grams, you have to do 15 grams. 15 grams times 2.5 kg divided by 1.015 kg. The answer which you are going to get over here, that will be in grams. Let me quickly calculate. 15 times 2.5 divided by 1.015 is going to give you 37. This is 37 grams. So the same way, I'm skipping this problem because we are going to solve that those questions when it comes to the MCQ session. Okay. Yeah. The next one, which we are going to solve over here, that would be the Henry's law. We might have seen so many things around us which follow Henry's law, but we have never thought that it comes under chemistry. Okay. It's just, I'll give you an example. You take a Coke bottle from the fridge and you see more bubbles coming out of it. Say you open the lid, or you open that the top, you have a lid, right? When you open it, you hear a sound. What's that? That's the carbon dioxide coming out. Okay. And if you have seen, if you have observed any Coca-Cola bottle or any cool drink bottle for that matter, this may not go as good as the bottle which is there. So only 3/4 of the drink will be here. You have the solution and here you have the gas, right? When you open this, this sound comes because this gas escapes. Now in case if you allow the solution to stand, like if you observe the solution, you see the bubbles coming out. Once the gas goes, there will be bubbles. Where are the bubbles coming from? They are coming from the solution. Where is the solution? Down. And what are those bubbles? That's the carbon dioxide. What is the state of that? That's a gas. Okay. Now, the same drink, you keep it outside for some time. When you open the lid, you don't see the same fizzing sound. You don't hear the same sound. It's very, very less. And if you see, there won't be bubbles coming out. What does that mean? So here, this is a gas which is carbon dioxide, which is undissolved. And here you have the carbon dioxide which is dissolved. And you put this top with greater pressure. It is sealed under greater pressure. So now you can say, more is the pressure applied, more will be the amount of gas which will be getting dissolved in the solution. So if you apply more pressure, more carbon dioxide dissolves in the solution. If you keep it open, the pressure is going to decrease. The carbon dioxide which is dissolved, that comes out. So lesser will be the dissolution. Or you can also say the solubility of a gas in the liquid. That means the carbon dioxide which is dissolved here is directly proportional to the solubility is directly proportional to the pressure of the gas above the liquid. What pressure you are applying above the liquid, that controls the solubility. That has some effect on the solubility. What will happen? We have a pictorial image over here. So at low pressure, there will be less number of particles which are dissolved, which are the gas. When you put a high pressure, more gas molecules are going to be there in the liquid. That means the pressure is directly proportional to solubility. We take the solubility in terms of mole fraction also. So P is directly proportional to X, or P is equal to KH into X, where KH is called as Henry's constant. Now, you have to remember, if you keep a constant at a given pressure, say I need this as 10, I can do it in two ways. 2 times 5 is 10, or it can be 5 times 2. Right. Now, if at a given pressure, if KH is less, X is more. Lower the KH value, higher will be its solubility, or higher is the KH value, lower will be its solubility. So, KH and X at a given temperature are inversely proportional. That's the reason. And also if you apply the temperature, Say for example, you keep this cool drink in the fridge, you get more amount of carbon dioxide dissolved. You keep it outside, carbon dioxide which is dissolved will come out. That's why if the temperature is more, the solubility of the gas in the liquid is less. That's why when the temperature increases in lakes, ponds and all, what is going to happen? The dissolved oxygen, which is already present in water, the aquatic species live by that dissolved oxygen, which is present in water, right? So the dissolved oxygen is going to be less in warm water compared to the cold water. But that's the reason why aquatic species are more comfortable to live in the cold water, because there will be more amount of dissolved oxygen. The solubility is more. The significance of Henry's law. What is that? The significance of Henry's law. Where do you apply this Henry's law? To increase the solubility of carbon dioxide, this we all know. The bottles are sealed with higher pressure. Higher is the pressure, higher will be the solubility. The second one, when people go for scuba diving, and there will be a cylinder which has certain gases. If they take the atmospheric gases, and if people used to fill that gas cylinder with the gas which is present in the atmosphere, it will contain more percentage, because in our atmosphere we have almost 70% of nitrogen. So there will be more nitrogen content than almost 20%, 21% of oxygen you have. So that will be the constitution. Those will be the gases which are present in the particular air. In case if they carry that cylinder, when you go down the sea, the pressure is more. So more oxygen or the more gaseous mixture is taken inside our body. And oxygen is used for biological activities. When they come up, the pressure decreases. So oxygen is being used, but the nitrogen is not being absorbed by our body. That tries to come out. That creates bend. That's the cramp like thing you will feel. And if you do the scuba diving, you are already inside the sea and you already have a fear in mind. And again, you have the cramp, you can't come out. So what do they do is they add helium to that mixture that's in the cylinder. So helium is not being absorbed by body as our body as our body takes nitrogen. So this bend, painful effect will be reduced. Then you have something called as anoxia. So you might have felt it when you climb very up. Say you go to some mountain, you go to trekking. When you reach the top, you feel like you need more oxygen to breathe, and you feel the giddiness and all. This is because when you go up, the pressure is going to decrease and your body is going to take less oxygen. The solubility of oxygen inside your blood will be less. That means you can't think properly. Okay, this is called as anoxia. So they have to carry the oxygen cylinders in that case. Then we go for the next topic, which is called as solubility. What is solubility? If you have any questions, please post in the comment box. Keep watching and keep supporting us, guys. Yeah, so far we don't have any comments. Yes. Now, okay, we are going to go for this one now. Yeah, the solubility. What is solubility? And you have to know the differences between the unsaturated, saturated, and the supersaturated solutions. You take some solute, you add it to a solvent. For example, take salt and dissolve it in water. It dissolves. You take 1 beaker of water, add 10 spoons of salt, it dissolves. Add 1 kg of salt to one, say not kg, 250 grams of salt to 1 cup of water. That may not dissolve completely, and you have some of the particles which are left behind, which are undissolved. So, and if you add little more to that, and if you are going to heat sometimes, then that becomes super saturated. Saturated is when you can't dissolve more salt. Super saturated is when whatever the component you have added that is going to crystallize instead of getting dissolved. So the concentration of the solute becomes very high in that case. So whenever you say solubility, in a given amount of solvent, say 100 grams of the solvent, what is the maximum amount of solute can be dissolved at that particular temperature? So if you increase the temperature, you have to mention the temperature, because if you change the temperature conditions, the solubility varies. So at a particular temperature, what is the maximum amount of solute you can dissolve in a particular solvent is called as solubility. So what it does, it depend on? It depends on the nature of the solute and the solvent. It depends on temperature, and also it depends on the pressure. We are going to see how this is going to affect the temperature and the pressure. Going to be affected by the temperature and the pressure. So let's take an example where we have solid dissolved in the liquid. I'll consider the condition where you have solid in a liquid. Like I said, when salt is dissolved in water. So salt is a solid. You're going to dissolve it in water. And when you dissolve the salt, there can be different type of reactions. So if you put the normal salt NaCl and if you put it in water, the salt dissolves. And if you have to add more amount of salt, and once it becomes a saturated solution, and if you have to dissolve more amount of salt, you have to heat. Okay, you have to heat. And then if you have ammonium chloride, when you add it to water, the test tube is going to become cool. So this is endothermic reaction. Sometimes the dissolution of salt in water, that can be endothermic or that can be exothermic. In those cases, the temperature is going to affect the solubility. But if you say the pressure affection, how the pressure is going to affect the solid in the liquid, since the solids are non-compressible and liquids are compressible but not as gases, then liquids are not also compressible, but compared to solids, you can compress the liquid a bit. So the solids in the liquid or the solubility of a solid in the liquid is not greatly affected by the changes of pressure. Okay, this is what I explained. And solid is added to a solvent and you get a solution. The concentration of the solute in the solvent is going to increase, and that is called as dissolution, and from which you get a solution, saturated solution, supersaturated solution. Now we have seen the solid which is dissolved in the liquid. Now we are going to see the gas dissolved in the liquid, or the liquid solutions. That's what we are going to discuss right now. So what happens when you dissolve a liquid in the liquid, or when you are going to dissolve gas in the liquid, which we are going to we have studied that under gases maybe, or we are going to see that later. Vapor pressure. There comes a concept called as vapor pressure. What is vapor pressure? As the name indicates, pressure created by the vapors is called as vapor pressure. From where did you get this vapor? Then you can say that you take any volatile liquid for that matter. What is volatile liquid? You know that the liquid which vaporizes volatile, vaporizes easily. For example, you can take petrol, or you can even take the kerosene. Is the kerosene volatile? Or better, you take the acetone. So all girls are very favorable to this example. Now, or you can even take water, but water is not that volatile. But for the concept, understanding of the concept, you can take that. So acetone is a volatile liquid. Now what you are going to do is take acetone in a container and close the container. The acetone is going to vaporize in the beginning. So you have the acetone in the liquid form, which is going to vaporize to gas. So you have the vapors over here. Vapors of what? Acetone. Now, after some time, there exists an equilibrium. Thus, the amount of liquid which is getting converted to the gas will be equal to the gas which is getting converted to the liquid. During this equilibrium condition, what is the pressure applied by this vapor on its own solution is called as vapor pressure. So generally we say vapor pressure as it is a pressure created by any gas on its own liquid when gas and the liquid are in equilibrium. That means amount of gas getting converted, or the rate of conversion of gas to liquid will be equal to the rate of conversion of liquid to gas. So the rate of evaporation is equal to a rate of condensation. Okay, how is this pressure created? So the molecules are going to hit the walls or among themselves. Now, what will happen if you open the container? If you open the container, the gases will go out, so there won't be any vapor pressure, or it will be very less, only on the surface. Now, this is called as vapor pressure, and we have to say vapor pressure in the pure state. If you take only one liquid, whatever the vapor pressure created by its own vapors on that particular liquid is called as vapor pressure of the pure solvent, and we put a symbol not over that. If you take water, for example, and if you close the container and then water vaporizes and the vapors, this vaporization, remember, this is a pure solvent we are taking, and this is going to vaporize. And so these are the molecules of water which are in the gaseous phase. Now, if you add the solute to that, say you have added some salt or sugar to that, so there will be interaction between the solute and the solvent. When there is interaction, what will happen? Say this is a condition where you have 10 members in the class, you don't know each other, there is no interaction between you. One person gets and goes out of the class, and the other person gets and goes out of the class, and the third person also gets and goes out of the class. Everyone can go out of the class. That is irrespective of the other molecules. But if you say you have a friend, so some of your friends have come to the class and they are attending the class. So what happens? You feel, oh, I shouldn't go. I may miss the class. This is an important class. So there is some bonding between you and your friend, who your friend is very studious. Though you want to go, you won't go. Right? And it is just remember, it is a class just before one day of the exam. You will never go. So there is some bonding or some connection between the solute and the solvent now, because of which the rate of evaporation decreases. That means when you add the solute to a pure solvent, then what do you expect over here? Then the vapor pressure, or the molecules of liquid which are getting converted to vapors, is less. When the number of molecules become less, the pressure created by them is going to decrease. That means the pure solvent will always have higher vapor pressure compared to the solution, because in solution you experience, or the molecules of the solvent are in interaction with the molecules of the solute. So solute solvent interaction reduces the vapor pressure. Now, if you increase the temperature of pure solvent, more molecules can get converted to the go to the gaseous phase. So the vaporization increases. So the vapor pressure is also going to increase. Now, we have one more concept over here. This is vapor pressure. And we have studied vapor pressure of the pure solvent when you have only the solvent. And also you have the vapor pressure of the mixture. What is that? Vapor pressure of the mixture. What is that? Vapor pressure of the mixture is called as, or it is also called as, partial vapor pressure. I'm going to erase all the writings on the slide so that I get more space. Yeah. So you have a pure solvent. This is a pure solvent. These are the solvent molecules, say water. And here you have the vapors, and those vapors create a vapor pressure, and that is called as PW. I'm writing because it is only water, not because it's a pure component. Okay, this is a pure component, only one component you have. Now you take water plus salt. So you have, along with the solvent, you have the solute, water plus salt. Again you have vapor, vapors and the vapor pressure. Now this will be more. This vapor pressure will be more compared to this because you've experienced the solvent-solute interaction. Now consider you have mixed, and remember the solute is not going to vaporize over here, only the water vaporizes. You have a mixture of water and acetone, so it's a volatile liquid. Now water can also evaporate, acetone can also evaporate. In the vapor phase you have vapors of water, so they create vapor pressure, and vapors of acetone as well, and that leads to the total pressure. That gives you the total pressure. So and this one Pw and Pa, these are not pure. Okay, this is in a mixture. So this are called as partial vapor pressure. So what is partial vapor pressure? In a mixture of liquids, volatile liquids, whatever the pressure created by one particular component in a mixture is called as partial vapor pressure. I can give you a better example. So you are the only person who is sitting in the class, and it's very early morning. No one has come to the class, or you don't know that there is no class. You have come to the school, and you are going to shout because you know that there is none, and you're going to shout. So the noise created by you can be compared with the vapor pressure of the pure component because you only are there. This is the first condition. This one. Then your friends have come to the class. All of you are there. And all of you are making noise. That's how you behave in the absence of the teacher, right? So you all are there in the class and everyone is shouting. So the total noise created by the class is noise created by you plus noise created by your first friend, noise created by your second friend, noise created by your third friend. So you sum it up and you are going to get the total noise created by the class. This is called as P total now. Everyone is contributing. So this is P total. And now this is the noise, the partial pressure of water. So you are contributing, your friend is contributing. All these are called as partial. Because in a mixture, in a group, what is your individual contribution? That is called as partial. The same way, in a mixture of liquids, what is the vapor pressure created by that particular component is its partial pressure in the mixture. When you add all the partial pressures, you are going to get the P total, which is the total pressure. Hope you understand that. Okay. Yeah, I'm moving ahead with the next one. Yeah, Raoult's law of partial vapor pressure. This is what we are going to discuss now. Say, for a solution of volatile liquids. Why volatile liquids you have to take? Because they should vaporize, right? If it is non-volatile liquid, it is not going to vaporize. When it doesn't vaporize, it won't give you any vapors. If there is no vapor pressure. You don't have the law at all. So for a solution of volatile liquids, the liquids should be volatile. The partial vapor pressure of each component, the vapor pressure created by one particular component in the mixture is partial vapor pressure of each component is directly proportional to its mole fraction. So in a class, the voice produced by you depends on how strong you are. Right? The same way. For a solution of volatile liquids, so you have taken two volatile liquids, say acetone and alcohol. So if you keep acetone alone, then I'll take the vapor pressure of this one as P1 naught. This is when it is kept alone. And when you keep this alone, the vapor pressure created by this is P2 naught. When you take in the mixture, the vapor pressure of acetone in the mixture will be P1. Vapor pressure of alcohol in the mixture will be P2. And in the solution, so you have here acetone and alcohol, which is in the liquid phase. You have a mixture over here. These two are in the liquid phase. Here you have the acetone and the alcohol, which are in the gaseous phase. These P1 and P2 refers to the vapor pressure in the gaseous phase, whereas acetone and alcohol, for that you have the mole fraction of acetone in the solution is x1, mole fraction of alcohol in the solution is x2. So according to this law, this P1, that's the partial vapor pressure of each component is directly proportional to its mole fraction x1, or you can also make it equal. This is a modified version of Henry's law. You can say instead of putting kh, you are putting P1 naught x1, where P1 naught is its that particular component's vapor pressure in the pure form. That's how we are going to explain the Henry's law. And P2 is equal to P2 naught x2. Now we can do P total. That's the total pressure created here. In it's a mixture of the P1 plus P2. So we have P1 is equal to P1 naught x1 plus P2 is equal to P2 naught x2, or P1 naught x1 which plus P2 naught, instead of x2 what you can put 1 minus x1, and you can rearrange this equation to different things. Now I'm going to continue this topic from Rawls law along with the explanation of graphs and couple of problems in the next class. Meanwhile, I want you to solve a couple of problems. If you are watching this, please support. Okay? Yeah. How are you going to explain this? What is this? Temperature dependent term among the following is this. We have already discussed. That's molarity. We have molarity is equal to, how do you define molarity as? Molarity is equal to number of moles of solute over volume of solution in liters. So with increase in temperature, volume increases, molarity comes down. Whereas molality, you have mass of the solvent, mole fraction, you have the moles, and weight percentage, you have the weight. So they don't get affected by the change in temperature. Okay. Hope you understand this. We'll go to the next question. So instead of giving P1 and P2, they have given PA and PB, where PA and PB are the components, the vapor pressures. So how do you find out? How do you find out this? Let me go ahead with the answers. PA and PB are the vapor pressure of the pure liquid components and A. So what do you get? PA is equal to PA naught XA. This is according to Rawls law, right? And PB is equal to PB naught into XB, where PB and PA are the partial vapor pressures, PA naught and the PB naught are the vapor pressure of the pure components. After this, what you're I'm sorry. After that, what you're going to do? The total, P total is equal to PA plus PB. That's nothing but PA naught XA plus PB naught XB. And they have taken XA outside everywhere. So if you have to take XA outside, if X represents the mole fraction of the component A, the total pressure of the solution would be. So how do you solve this? Okay. PA, I'll just not put a not XA plus PB naught. XB is nothing but 1 minus XA. So it's PA naught XA plus PB naught minus PB naught XA. Now if I take PB here, PB naught, and if I put, yeah, XA terms I can put together. If I take XA term together plus XA, I have to written outside. If it is XA, then it is PB A naught minus PB naught. This is how you solve. So it's PB plus XA PA. Since we have taken A outside, it's A minus B. So the correct answer would be option 2. Instead of not, you have to use the proper A and B terms. An aqueous solution of 1 is 1.0 molal in Ki. So the concentration is given of Ki in this aqueous solution. Which change will cause the vapor pressure of the solution to increase? How you can increase the vapor pressure of the solution? Addition of NaCl. So if you add the NaCl, there will be more again solute and the solvent interaction that won't increase the vapor pressure, that is going to decrease. Again, the addition of Na2SO4 will be the same, and addition of 1 molal Ki, again the same concentration will have the same effect on the another solution. You are mixing two solutions having equal concentration. This is not no way going to increase vapor pressure. And the addition of water, if you dilute the solution, if you are going to add water, if you're going to dilute the solution, then there will be decreased solute solvent interaction and the solvent can vaporize easily, so there will be more vapor pressure. So the addition of water will be the right answer. The mole fraction of the solute in 1 molal aqueous solution is. What is 1 molal aqueous solution? They have given molality. We have the formula molality is equal to number of moles divided by mass of solvent in kg. So molality is 1 molal, mass of the solvent in kg, so that should be kgs in 1 kg of the solvent. Okay, you take 1 kg of the solvent, so the number of moles, if you take it as number of moles of solute as 1, so the mole fraction of the solute, so XA, let it be, is equal to number of moles of the solute is 1, number of the moles of solute divided by the number of moles of water. What is the mass of water? 1 kg divided by its mass is 1 kg divided by molar mass, that's 18. So how do you calculate it? Hope you get it. Let me calculate it really quick. So it's 1000 divided by 18, that's 55.55. 1 divided by 56.55, that's almost equal to 0.018. Option 2 would be the right answer. So you have 1 kg of the solvent, 1 molar solution in the sense. So number of moles, when you say 1 molar aqueous solution, the number of moles of the solute becomes 1. So the mole fraction is number of moles of solute divided by number of moles of solute plus number of moles of solvent. Solvent is 1000 grams because it's 1 kg, 1 molar solution divided by its molar mass. That's going to be 0.0176. That's nothing but 0.018. The next question we have over here is this one. Yeah, the next question, no one is answering, and please watch and put your answers in the comment section whenever you watch. So what it would be, 5 cm cube of acetone is added to 100 cm cube of water. Vapor pressure of water over the solution will be. So when acetone is added to water, this we can discuss when it comes to the azeotropic mixture. So 5 cm cube of acetone and is added to water. So what happens to the vapor pressure of water? What do you think it is? So this is left your thinking. We'll come back with the answer in the next class, and we are going to take the acetone water mixture in the next class as well. So keep watching, keep supporting. Have a good day. Thank you for watching.